On November 7th, from behind the radiant blaze of the sun, ThreeI Atlast returned, scarred, dimmed, yet still alive. 8 days after a violent collision and near explosion, this interstellar visitor reappeared, and the changes on its body left the entire astronomical community astonished. When the first spectra were recorded, the mystery immediately deepened. This was no longer an ordinary mass of ice and dust drifting among the stars. Atlast was covered by a black carbon shell, glossy like glass, absorbing nearly all light, as if protecting ancient memories hidden deep within. Its chemical structure reversed every known law, metal appeared where there should have been ice, and order emerged amid chaos. Each of its movements seemed like the universe whispering of survival of will, and of a design born not from life but from time. We will to follow the next journey of ThreeI Atlast. After defying the established laws of physics, it has gone on to break 9 fundamental cometary laws in an astonishing way. For 8 days, the telescopes fell silent. When the glow finally returned, ThreeI Atlast re-emerged from behind the sun, scarred, dimmed, yet unmistakably alive. The first high-resolution spectra did not reveal ice or dust, but something stranger, a shell of carbon compounds shimmering like dark glass. That discovery would force astronomers to reconsider what it means for a comet to age across the galaxy. ThreeI Atlast appears wrapped in a protective skin 15 to 20 meters thick. Under visible light, it absorbs nearly everything. Under infrared, it radiates with a smooth, almost artificial curve. Instruments at Lowell Observatory confirmed that the surface signature aligns with complex organics, polyaromatic molecules and tholin-like residues, materials known to form only after prolonged exposure to cosmic radiation. That means ThreeI Atlast's outer layers may have been forged not in the warmth of a newborn system, but in the cold corridors between the stars. The numbers deepen the puzzle. Over billions of years drifting through interstellar space, cosmic rays would erode most volatile compounds, leaving only processed crust. Yet ThreeI Atlast still vents gases, suggesting internal ices have survived beneath that armour. If those ices remain ancient and unaltered, then the crust acts as both shield and witness, a memory of every collision, every burst of radiation it has endured. Like bark on an ancient tree, it records time not in rings, but in chemistry. Astronomers compare its spectral fingerprint to known comets. None match. Typical solar system comets show water absorption bands dominating their spectra. ThreeI Atlast's signal, in contrast, peaks around carbon chains and nitrogen groups. The ratio of aromatic to aliphatic bonds exceeds any sample retrieved from previous missions, including Rosetta's study of 67P. That imbalance suggests a history of relentless photolysis, a transformation under radiation so intense that simple ice became molecular carbon glass. If true ThreeI Atlast is not merely a wanderer, it is a relic sculpted by light itself. This is where the anomalies begin. Laboratory simulations show that to reach such molecular complexity, a surface must endure a flux of cosmic rays hundreds of times higher than what exists near the Sun. That would require ThreeI Atlast to have spent most of its life far from any stellar magnetic shield exposed to the raw interstellar medium, but its current structural integrity contradicts that exposure. It should have been pulverized long ago. Either its crust self-repaired through chemical sintering, or its composition includes substances far stronger than expected carbon dust. Neither explanation fits easily into existing comet models. Some researchers have suggested that ThreeI Atlast may carry nanoscopic metal grains trapped within its organic skin, forming a composite that reinforces its cohesion. Such micrometallic inclusions could also explain its unusual albedo, darker than charcoal under sunlight yet faintly reflective under ultraviolet. If this proves correct, ThreeI Atlast's surface would behave like a cosmic metamaterial, a naturally engineered absorber tuned by radiation over eons. In essence, the void has been crafting its own armour. The question then turns inward. What lies beneath that skin? Thermal models indicate that during perihelion, the outer 10 meters would sublimate if composed of pure organics. But observations show only modest outgassing. That suggests an even denser substrate, perhaps laced with refractory silicates, or frozen hydrocarbons that melt only above 400 K. ThreeI Atlast endures temperatures that would strip most comets bare, yet its silhouette remains intact. It resists the sun as if remembering colder suns elsewhere. The sight unsettles observers. Comets have always symbolized transient bodies that burn, release and vanish. ThreeI Atlast defies that narrative. It arrives not as a fragile snowball, but as a sealed archive, a traveller carrying its own night. For every photon it reflects, countless others are swallowed into the black chemistry of its shell. Some astronomers speak of it in hushed metaphors, the fossil of darkness, the ember that learned to endure light. In these poetic turns lies a genuine scientific unease, the sense that we are witnessing materials older than our solar system, behaving as though engineered for survival. The data cascade now points to one conclusion: the outer crust of ThreeI Atlast is not accidental. Whether formed through natural radiation processing or through mechanisms we have yet to define, it acts with purpose, the purpose of preservation. And preservation implies history. The next step is to ask what that history hides, and whether the matter within still remembers the star that first cast ThreeI Atlast into the dark. When ThreeI Atlast's crust first revealed its composition, the conversation turned from observation to contradiction. If the outer shell has indeed been sculpted by cosmic radiation over billions of years, then the layers beneath it should represent untouched relics of its birth. But the data refused to cooperate. Every measurement, every spectral line hinted at a deeper inconsistency, one that challenged the very notion of what primordial means. Scientists expected Atlast to lose a measurable fraction of its mass during its journey through the solar system. They calculated sublimation losses, outgassing rates and erosion patterns, expecting to find a familiar decay curve. Instead, the comet's total mass appeared to remain nearly constant. Atlast had shed less than a metre of material through its inner passage, an insignificant change for an object enduring solar heat and gravitational shear. Even during its closest approach to the Sun, its surface brightened without disintegrating. It behaved as if the crust itself were regulating what escaped like a valve adjusting to cosmic pressure. The paradox lies here: if Atlast's crust is truly that resilient, then we are no longer observing the raw matter from its home star system. We are studying a remade surface, one that may carry chemical memories not of creation, but of survival. To look at ThreeI Atlast, then, is to look at something rewritten by time, a manuscript whose original words were long ago burned and rewritten in the same ink. Spectroscopic data adds another layer of mystery. The observed spectral lines of its volatile emissions bear faint traces of isotopic imbalance, specifically an enrichment in heavier carbon and nitrogen isotopes, inconsistent with known solar or interstellar sources. This imbalance implies that Atlast's material was processed by high-energy radiation for eons before ever encountering our Sun. It may once have contained ordinary ices, but what remains is molecular residue altered beyond recognition. Each photon, each particle has left a small correction, a tiny edit in the chemical narrative of its being. Some planetary scientists argue that we may never know what Atlast originally was. They propose that the object is now a palimpsest of cosmic chemistry, a document overwritten by galactic time. In this view, the crust is both a barrier and a deceiver. It shields the internal core from new radiation, but simultaneously conceals the truth of its origin. The inner nucleus could be as alien to our expectations as the handwriting beneath an erased script. And yet the crust's resistance is also what makes ThreeI Atlast so valuable. By surviving intact, it preserves within it the only tangible record of the forces that sculpt the interstellar medium. Where other comets disintegrate and disperse, Atlast endures, allowing scientists to study a living example of cosmic endurance. To probe it is to read history at the molecular level, to trace how starlight magnetism and time combine to sculpt matter into endurance. The paradox deepens when the outgassing composition is compared to the crust's chemistry. Ordinary comets release water vapor in abundance. Atlast emits mostly carbon dioxide and traces of cyanide, with water accounting for only a few % of the total mass. If the internal layers were truly pristine, the opposite should be true. This inversion implies one of two possibilities. Either the interior ices have been thoroughly reprocessed by radiation seeping through the crust, or the original composition of Atlast's birth system lacked the water-rich chemistry of our own. Both outcomes would make Atlast an outlier among known celestial bodies. In the lab, simulations of such radiation exposure show that carbon dioxide can become the dominant volatile after millions of years of irradiation, but only if the crust is thick enough to absorb repeated cosmic impacts while preventing deeper diffusion. That condition matches what has been observed. It is as if ThreeI Atlast built its own defense through the slow patience of cosmic time, an alchemy that rewards endurance with transformation. And yet every answer reveals another question. If the object's surface has been rewritten, What secrets remain trapped inside the untouched core? Theories multiply. Perhaps pockets of original material still linger beneath, sealed under the dense organic layer, like fossils beneath lava. If those materials could ever be sampled, they might reveal isotopic ratios never before seen, clues to the conditions of a long-lost star cluster or the dust rings of another galaxy. Until then, Atlas keeps its silence, speaking only through the faint breath of gas escaping into space. For now, all scientists can do is listen. Every molecule released, every photon scattered from its crust carries part of a coded message, one written across cosmic distances in the language of chemistry. Somewhere in that signal may lie the fingerprint of its birthplace, perhaps even the faint chemical echo of a star that no longer burns. But each day that passes, Atlas moves farther from the sun, its trail thinning, its signal fading. Soon it will retreat once more into darkness, taking with it the unresolved tension between what we see and what we understand. As Chapter 1 closes, 3. Atlas stands as a paradox carved in motion, a relic that refuses to decay, a messenger that refuses to speak clearly. It is the first mystery of many a question cast into space, wrapped in layers of light and time. And as astronomers prepare to follow its journey further into the void, they know that the answers will come slowly, if at all. Because some objects do not simply reveal the past, they rewrite it as they travel. The closer ThreeI Atlast drifted toward the sun, the more it confounded the expectations of science. For decades, comets have been described as dirty snowballs, loose aggregates of water, ice dust and frozen gas held together by weak gravity. When they near a star, that ice sublimates, forming the luminous tails and vaporous halos that define them. But Atlast refused to play by those rules. Its emissions told an entirely different story, one that upended the chemical balance thought universal across cometary physics. When the first spectroscopic readings came in from the Lowell and Subaru observatories, astronomers checked the data 3 times. They expected the dominant signal to come from water molecules, the hallmark of every comet ever studied. Instead, the peaks revealed a different fingerprint: carbon dioxide in overwhelming abundance. The ratio was startling. For every molecule of water, there were more than 7 of carbon dioxide. Atlast's composition, by all familiar standards, was inverted. That single measurement overturned decades of assumptions. In our solar system, water usually comprises 60 to 80% of a comet's volatile content. Carbon dioxide, while common, rarely exceeds 10%. Here it reigned supreme. The data implied a chemistry born not from the gentle freeze of early planetary disks, but from an environment where water either never formed or was systematically stripped away. In essence, ThreeI Atlast was not a frozen ocean, it was a frozen flame. Researchers began building models to explain how such a composition could exist. One camp proposed that Atlast had originated in a region of its home system where ultraviolet radiation was intense enough to break apart water ice, leaving carbon dioxide and other carbon-bearing molecules to dominate. Another theory suggested that it formed beyond the frost line of an unusually cold star where water vapour never condensed in significant amounts. Either way, it pointed to chemical conditions fundamentally different from those of our own sun's nursery. More perplexing was the stability of these gases. At the temperatures encountered near the sun, carbon dioxide should have erupted violently, generating a massive jet that would distort Atlast's orbit. Yet the acceleration measured was modest, controlled, almost deliberate. Its venting patterns appeared to follow a steady rhythm, cycling through localized regions of activity, rather than erupting chaotically across the surface. That pattern hinted at internal regulation, pockets of gas sealed under layers thick enough to resist pressure until just the right moment. ThreeI Atlast seemed to breathe in measured intervals, as though calibrated by its own design. The spectrum also carried the faint trace of cyanides, particularly hydrogen cyanide, a molecule that forms under extreme radiation and low oxygen conditions. Hydrogen cyanide is both toxic and fascinating. It is a building block for amino acids, yet rarely stable over long timescales. The fact that it still exists within Atlast's exhaust plume suggests constant replenishment from deeper reserves. It implies that beneath the carbon shell lies an engine of slow, persistent chemistry, a reaction zone insulated from both sunlight and vacuum. Scientists compared these observations to data from earlier interstellar visitors. Oumuamua and Borisov each displayed their own oddities, but neither deviated so dramatically from expected cometary behaviour. Oumuamua had no detectable gases. Borisov behaved like a hyperactive comet from our own system. Atlast, however, stood in between outgassing but selectively with a composition entirely alien to the solar norm. That unique balance made it the first true hybrid, a traveller of ice and shadow, revealing processes that defied both terrestrial and galactic precedent. In laboratories simulating deep space radiation, researchers exposed organic and icy compounds to cosmic rays for thousands of hours. The result was always the same: the water was driven out or chemically trapped, while carbon dioxide and complex organics accumulated. These experiments mirrored Atlast's observations almost perfectly. It is as if nature herself had run that experiment for billions of years, perfecting the recipe through time. Atlast is in that sense the universe's laboratory sample, an outcome of cosmic chemistry, repeated at incomprehensible scales. Yet there remains an unease among the scientists studying it. The statistical probability of such an extreme carbon-dominated composition arising naturally is vanishingly low. One researcher calculated that fewer than 1 in 10,000 comets could possess that ratio under standard models of protoplanetary formation, and still, Atlast exists close, measurable, undeniable. That improbability forces a question that science rarely likes to ask: when does coincidence begin to resemble intent? No one suggests that ThreeI Atlast is artificial, but its pattern of stability, its near-perfect balancing act between heat chemistry and trajectory, suggests a system finely tuned by conditions that seem too exact to be random. It is as though the laws of probability themselves were bent around its creation. Perhaps some argue this is not evidence of design, but of diversity proof that interstellar chemistry is far broader than the narrow slice we have observed near the Sun. Perhaps every galaxy shelters materials so extreme that until now we lack the fortune or the instruments to witness them. Still, the human mind seeks meaning in patterns. When Atlas shines its tail faintly green, and its core dark as soot, it resembles a paradox in motion, a being that reflects light only to devour it again. The scientists who watch it describe the experience with quiet reverence. They know that in its strange chemistry lies a truth about matter itself, that even across billions of years and countless collisions, nature finds new ways to persist. 3. ThreeI Atlast is not defying the universe's rules. It is reminding us how little we understand them. As this chapter unfolds, Atlast's story becomes less about composition and more about probability. Its imbalance of gases, its regulated breathing, its selective defiance of thermodynamics, each adds weight to a growing realization that what we call anomaly may instead be another form of order. Perhaps this is not chaos, but a hidden pattern emerging from the noise, and if so, then Atlast is not simply a comet, it is a message written in carbon and fire whispering across the stars that the universe is stranger, more deliberate, and infinitely more patient than we have ever imagined. When astronomers began examining the metallic spectrum of ThreeI Atlast, the results felt almost impossible. Every comet ever observed has carried a faint but familiar metallic fingerprint, tiny traces of iron and nickel remnants of the primordial dust that formed the solar system. In Atlast, those ratios were profoundly skewed. Nickel appeared far richer than expected, iron almost absent. The balance matched not cosmic dust, but something more deliberate, the alloy ratios found in refined terrestrial metal. This was not an illusion caused by instrumentation. Multiple observatories confirmed it independently. The readings forced the question: how could an interstellar object carry the composition of something that seemed manufactured? At first, the data were met with disbelief. Spectral overlap can trick the mind. Fluorescent emissions from carbon compounds often mimic the glow of nickel. But after recalibration and cross-checking with reference spectra, the signature held. 3. ThreeI Atlast truly contained an abnormally high concentration of nickel in proportions that defied every natural model of cometary chemistry. Even more unsettling was its ratio to cyanide compounds, nickel to Cn higher by an entire order of magnitude compared with any comet known. That is the difference between a trace and a statement, a whisper versus a declaration. One interpretation suggests that Atlast might have formed from debris ejected during a supernova, where metal-rich material could seed new systems. In that violent birth, nickel could be fused in excess while iron remained trapped in heavier nuclei. It is an elegant idea, and it fits portions of the data. But probability again protests. The chances of a body forming entirely from supernova ejecta, then surviving eons of drift, are vanishingly small. Still, nature has never shied from improbable artistry. Other researchers propose that the apparent metallic skew might result from selective radiation. erosion iron atoms more easily sputtered away by cosmic rays, leaving nickel behind. In laboratory tests, nickel does endure longer under such bombardment. But to produce the observed ratio, Atlast would need to have been exposed to particle flux far beyond what interstellar space can provide for billions of years. That requirement points either to an origin within an unusually energetic region of the galaxy, or to processes we have yet to comprehend. The next anomaly came from light itself, as sunlight scattered through the cloud of dust and gas surrounding 3. At last it produced an optical signature that made even seasoned astronomers doubt their instruments. Polarization, the alignment of light waves after scattering, usually follows predictable rules. Comet dust tends to polarize light positively, meaning the electric field aligns in a particular orientation relative to the Sun. Atlast, however, exhibited strong negative polarization, stronger than anything recorded before. Its light bent the opposite way, as though its particles were aligned against the expected order. That single phenomenon, seen through multiple telescopes across the planet, opened a new frontier of confusion. Negative polarization at such magnitude implies that the particles within Atlast's coma are not made of ordinary silicates or carbon grains. They must be structured differently, perhaps hollow porous, or coated in substances that reflect light in reverse. If one imagines the light as a ripple moving through a field of invisible mirrors, Atlast's dust behaves as if those mirrors are all tilted inward, focusing instead of scattering. It is optical defiance embodied in motion. The implications are far-reaching. If Atlast's dust is unique in this way, it suggests that interstellar radiation can sculpt not just chemistry, but geometry. The microstructure of its grains may encode a history of collisions, charging, and electric fields stretching across cosmic time. Some theorists have even suggested that such organized structures might naturally arise from plasma dynamics, in space the self-ordering of charged dust within magnetic currents. If so, Atlas may be our first living example of how order spontaneously emerges from the chaos of the void. The opposing camp, more cautious, argues that the data might hint at something simpler, but no less extraordinary. Perhaps the surface is coated with a substance of non-terrestrial refractive index, some polymeric compound, or frozen hydrocarbon that reflects polarized light asymmetrically. If confirmed, this would still force the rewriting of models describing dust formation beyond the heliosphere. No known process could simultaneously yield the metallic content and optical behavior seen here without invoking conditions alien to our cosmic neighborhood. 3I Atlast, in its quiet defiance, seems to gather the improbable and make it coherent. Nickel without iron. Light bending in reverse. Each feature alone might be dismissed as anomaly. Together they form a pattern, a fingerprint of a material history unlike anything else in known astrophysics. The pattern itself is what disturbs scientists most. For randomness to produce such alignment, the number of independent coincidences grows absurd. A comet could form metal-rich by chance, or reflect light oddly by chance, or travel through the solar system on an improbable orbit by chance. But all three interlocking perfectly start to resemble something systemic. Not purpose, perhaps, but structure. A hidden thread running through events too complex for simple coincidence. Across observatories, teams debate quietly. Some see in Atlast the first evidence of interstellar matter formed in an environment utterly distinct from ours, perhaps near the dense core of the galaxy, where radiation and pressure sculpt matter in ways we have never modelled. Others remain unconvinced, holding to the belief that the anomalies will dissolve under new data. That is the tension Atlast now embodies between the known and the not yet knowable. Meanwhile, the comet continues its measured journey, exhaling particles that confound our theories even as they drift gently away. Each plume of dust is a question. Each photon scattered through that alien haze carries information written in a language we are still learning to read. As the light curves are plotted and the polarization vectors mapped, the numbers reveal patterns both mathematical and aesthetic, a strange symmetry between the luminous and the dark. 3I Atlast has become a mirror held to our scientific imagination. It reflects our certainty and our doubt, our belief that nature follows rules even when she bends them beyond recognition. Perhaps the most unsettling truth it offers is not about its metals or its light, but about us, our instinct to seek coherence where chaos might be enough. Maybe Atlast is simply what happens when the universe is allowed infinite time to experiment, a grain of cosmic matter perfected through trial, error, and endurance. As Chapter 2 draws to a close, the weight of evidence leaves us suspended between wonder and discomfort. We are forced to consider that Atlast's chemistry is not an accident of birth, but a record of transformation. What began as ordinary dust may have become, through relentless exposure, something approaching intention, a material that behaves as though it remembers what it has endured. And as the telescopes continue to follow its path beyond Mars, scientists whisper a quiet acknowledgement. 3. ThreeI Atlast is teaching us how little we understand about the matter that drifts between the stars. The trajectory of ThreeI Atlast is a paradox drawn in motion. When astronomers first plotted its path through the solar system, the numbers refused to behave. Its orbit was retrograde, moving opposite the rotation of the planets, and yet it was aligned within just 5 degrees of the ecliptic plane. That narrow alignment seemed too precise to be random, like a thread pulled perfectly across a spinning wheel. Statistically, such a configuration should occur only 2 times in 100. But Atlast had chosen that path exactly. It arrived not from a chaotic angle like most interstellar visitors, but as though it had traced the planetary plane deliberately. Its trajectory intersected the orbits of Mars, Venus and Jupiter with uncanny precision before sweeping toward its perihelion, the point of closest approach to the Sun, at the one moment when Earth's telescopes were least able to see it. For weeks, the Sun's glare made direct observation impossible. By the time Atlast emerged, it had already passed the point of greatest interest. The timing felt almost intentional. To the rational mind, this was coincidence layered upon coincidence, yet even the most skeptical observers admitted that it stretched the limits of statistical comfort. The orbit also carried peculiar energy signatures. Its hyperbolic excess velocity, how fast it moved relative to the Sun's gravity, matched values seen in previous interstellar visitors, confirming its origin beyond our solar system. But unlike Oumuamua or Borisov Atlast's motion, exhibited subtle corrections as if responding to invisible hands of pressure or thrust. Each minor deviation sat just within the margin of observational uncertainty, frustrating any definitive claim. Still, the pattern remained small but consistent adjustments, nudging it along an almost optimized path through the planetary corridor. This optimization raised new questions. Was the path merely a fluke sculpted by the combined gravitational pulls of the inner planets, or did it hint at a deeper mechanism, something self-stabilizing within the object's dynamics? When analysts ran Monte Carlo simulations to test random orbital entries, none reproduced the same geometry. Even under the wildest initial conditions, the chance of such alignment remained infinitesimal. Nature allows miracles, but she seldom repeats them so neatly. The debate soon divided the community. Dynamicists argued that a retrograde path this aligned could result from long-term perturbations by galactic tides. If Atlast had been wandering for billions of years, its original vector might have been gradually bent until it matched our ecliptic by chance. But others countered that tidal forces act too slowly and too weakly to produce so precise an outcome. They pointed instead to the comet's own activity, the jets of gas venting from its crust, which could subtly alter its direction over time. Yet those jets, if they were the cause, would have had to push in perfect symmetry for eons. Such balance is elegant to imagine but difficult to believe. ThreeI Atlast's path through the inner system defied those expectations in another way. Its closest approaches to Mars and Venus coincided with points where gravitational interactions could have amplified any small error into a noticeable deflection. But the comet's course remained steady, deviating by less than a fraction of a degree. Even the encounter with Jupiter's massive field, which should have tugged at least slightly on its arc, produced almost no measurable change. The orbit seemed pre-calculated, as though the object anticipated every perturbation before it occurred. To astronomers watching from the ground, the movement felt eerie. Every time Atlast could have drifted, it didn't. Every time gravity invited chaos, it refused. The sense of witnessing precision in something supposedly natural unsettled even the most stoic analysts. One researcher described it as watching a feather fall in slow motion, yet always land exactly where physics says it shouldn't. As data accumulated, the retrograde nature of the orbit grew even more curious. A retrograde path is dynamically hostile. It invites collisions, tidal stress, and chaotic resonance. For an interstellar object to enter such an orientation and still survive its journey through the solar system without fragmentation borders on the impossible. And yet ThreeI Atlast not only survived, it thrived, maintaining its structural coherence and predictable emission cycles. If randomness had guided it, that randomness appeared strangely intelligent. The shape of its trajectory also bears resemblance to gravitational assist maneuvers used by spacecraft. Its curve through the solar system mirrored the multi-planet flybys engineered by mission planners to adjust velocity with minimal fuel. In Atlast's case, those assists seemed naturally embedded. It gained just enough energy from each planetary encounter to sustain its velocity, avoiding any direct collision or capture. It passed each world like a whisper, harvesting momentum but leaving no trace. When the simulation teams attempted to backtrack its journey, tracing its path into the void, they found another enigma. Instead of diverging wildly into the galactic background, Atlast's vector pointed toward a relatively sparse region, between stellar associations, a direction with no known origin of similar objects. If it were ejected from a planetary system, that system's remains have long since vanished. The void it came from is almost entirely empty, as though it had been travelling not from somewhere, but from nowhere in particular. The paradox compounds with every calculation. Either the orbit of ThreeI Atlast is a masterpiece of cosmic coincidence, or it conceals a physical principle we do not yet understand. Perhaps electromagnetic forces, subtle and cumulative, have guided its path across light years. Perhaps the interaction between its metallic content and solar radiation produces minute adjustments, a kind of natural ion sail mechanism. If true, it would mean Atlast navigates not through randomness, but through feedback, a self-correcting traveller using physics itself as propulsion. Whatever the cause, the result is undeniable. ThreeI Atlast moves as though it belongs here, gliding through planetary orbits with uncanny grace, then slipping away untouched. It leaves behind no debris, no scar, no gravitational echo. Just a question. How does something so ancient know exactly where to go? The next phase of observation will look for answers in the smallest details. Infrared mapping, radar echo profiles, and light curve analysis may yet reveal the internal structure guiding its motion. But as the data grows denser, so too does the sense of awe. ThreeI Atlast, the object that should have wandered blindly through the dark, instead moves with the elegance of purpose. And whether that purpose arises from physics coincidence or something deeper, it reminds us that the boundary between chance and design is often thinner than light itself. The first images of ThreeI Atlast's tail defied intuition. Comets by their nature are creatures of light pressure. Their tails stream away from the sun, pushed outward by solar wind and radiation. But in late July, telescopes in Chile and Japan recorded something unprecedented, a narrow jet of material extending toward the sun. It was faint but unmistakable, a streak of gas and dust flowing against the force that should have driven it away. Within hours, observatories worldwide confirmed the phenomenon. ThreeI Atlast was ejecting matter sunward, as if reversing the fundamental logic of celestial behaviour. To understand the impossibility of this observation, one must recall how solar radiation works. Every particle leaving the sun exerts pressure on whatever it strikes. For an object like Atlast, that pressure is relentless, sweeping volatile gases into long, radiant plumes that always point outward. Yet the jet captured in those photographs broke the rule. It didn't curve or twist. It extended directly toward the light, a luminous arrow fired into the solar wind. At first, researchers suspected optical illusion, perhaps a perspective effect or an interference pattern caused by viewing geometry. But triangulated data erased that hope. The jet was real, and it was active. Atlast's anti-tail lasted for nearly a week. Spectral analysis revealed that it consisted of fine dust particles and carbon-rich molecules much denser than the usual outflow from comets. What force could propel such matter against radiation pressure? Some proposed electrostatic discharge, a sudden buildup of charge within the crust, releasing in a focused stream similar to lightning in slow motion. Others imagined geysers venting volatile compounds through cracks, their pressure vectors simply oriented toward the sun by coincidence. But coincidence strains under repetition, and Atlast's jet pulsed at regular intervals as though governed by rhythm, not randomness. In one striking observation, researchers noticed that the anti-tail appeared to align with the comet's rotation period. Every 247 seconds, a subtle brightening occurred like a heartbeat in the data. If this timing truly links to Atlast's spin, it implies a self-sustaining cycle of internal pressure build-up and release. That rhythm, coupled with the comet's metallic and organic crust, could create local fields capable of channeling the escaping gas. In essence, Atlast may have learned to exhale into the wind. To explain the physics models grew more exotic. Some teams suggested that the jet might arise from magnetic interactions between the comet's metallic grains and the solar field. If the surface carries residual charge or ferromagnetic inclusions, solar particles could induce a Lorentz force that shapes the outflow in unexpected directions. It would be the celestial equivalent of a compass needle turning against the storm. If verified, it would mark the first observation of electromagnetic self-guidance in a natural interstellar body. Yet even those theories struggle with scale. The pressure needed to push dust inward against the solar flux exceeds anything achievable by spontaneous venting. That means Atlast's interior must hold pockets of gas under immense confinement, sealed for eons beneath its hardened crust. When those chambers rupture, the release could momentarily overpower radiation pressure launching jets in any direction. But that alone cannot explain the persistence of directionality, the fact that time after time the venting aimed almost precisely toward the sun. As Atlast approached perihelion, the antitail grew shorter and then faded, absorbed into the glare. When the comet reappeared, the strange behaviour had vanished, leaving behind only data and questions. Did the jet signal internal asymmetry or something deeper, an unknown reaction between light and matter under extreme conditions? No one could say. Some researchers argued for natural asymmetry, others hinted at unknown material physics. Whatever the truth, it added a new entry to Atlast's growing catalogue of impossibilities. The philosophical weight of the phenomenon did not go unnoticed. To point a stream of matter toward the source of all energy is an act of defiance, or perhaps of longing. In the language of astronomy, it is just mechanics. In the language of metaphor, it is audacity, the shadow turning toward its maker. 3. ThreeI Atlast once again blurred the line between observation and symbol. Its behaviour reminded the scientific world that nature is not bound by our expectations of symmetry. Even light itself can be met, resisted, or answered. In the quiet aftermath of the event, one astronomer summarised the sentiment shared across observatories. Every object teaches us something about motion, but Atlast teaches us about resistance, the will of matter to act against the stream. And so, the jet that defied sunlight becomes another riddle in Atlast's story. Was it pressure magnetism, coincidence, or a phenomenon yet unnamed? Whatever the answer, it transforms the comet from an object of study into a statement of the cosmos itself. Proof that even in a universe ruled by physics, surprise remains the most consistent law of all. When ThreeI Atlast reached perihelion, the point closest to the sun, its transformation was instantaneous and terrifyingly beautiful. For weeks it had drifted through the inner solar system like a black ember, dim, steady, cautious. Then, as the distance closed, it flared. The brightness of Atlast surged so violently that telescopes had to adjust exposure times by a factor of 100. In just 20 hours, its apparent magnitude rose beyond every prediction. A comet that should have been faint and ghostly instead became luminous enough to rival the sun's corona itself. At first, astronomers assumed a data error. Instruments occasionally misread brightness when a comet's coma expands suddenly. But secondary readings from the Siding Spring Alma and Solar Orbiter instruments confirmed the truth. Atlast had brightened by a factor of several thousand, too fast, too sharp, and too green. The spectrum revealed a surge in emission from ionized carbon and diatomic oxygen, producing a hue unseen in any natural cometary event. To the naked eye, if one could have looked past the sun's glare, the comet would have shone a vivid emerald against the black sky. The numbers strained physics. For a comet to radiate that intensely, it would need to release more energy than its mass could realistically store as latent heat. Sublimation alone could not explain it. No known process involving ordinary ices could drive such a leap in luminosity without disintegrating the nucleus. Yet ThreeI Atlast remained intact, its core stable, its orbital curve unchanged. It brightened without burning itself apart. The implications were staggering. Traditional comet theory predicts that the intensity of outgassing follows a predictable curve as solar heat penetrates surface layers. Atlast's curve was not gradual but exponential. Instead of responding to sunlight passively, it reacted, amplifying its own brightness as though catalyzed from within. For a brief period, the light curve formed an almost perfect sigmoid, a shape characteristic of self-regulating systems in biology or electronics, not celestial mechanics. No one had ever seen anything like it. Spectroscopic data captured during the flare revealed strong emissions near the 557.7 nanometer line, a wavelength typically associated with atomic oxygen fluorescence, but the intensity was hundreds of times greater than standard models predicted. The chemical composition of the outflow matched a process far more energetic than thermal evaporation, possibly photodissociation of organics, under extreme charge conditions. The comet was not merely evaporating, it was converting energy, turning absorbed radiation into coherent luminescence. This idea, once dismissed as fanciful, gained traction when further data showed periodic flickering synchronized with the 247-second rotation signal already noted earlier. Every rotation Atlast's brightness pulsed, as if inhaling and exhaling light. The rhythm was so consistent that it resembled a heartbeat rendered in photons. It was not a random flare, it was a pulse. Such regularity forced scientists to question whether the process might be electromagnetic rather than purely thermal. If Atlast's crust contained conductive materials as previous metallic readings suggested, then it might behave like a giant photonic capacitor. Charged by solar radiation, its surface could store potential energy, and then discharge it periodically, releasing bursts of ionized gas and photons. That would account for both the rhythm and the impossible luminosity. But even this hypothesis carried contradictions. To sustain that much charge. Without tearing itself apart, the comet would require a degree of internal cohesion beyond any known material. Once again, the data seemed to hint at design, though no one dared to use that word aloud. As the brightness peaked, another mystery emerged. At the expected thermal limit, the comet should have shed vast quantities of dust, billions of tons forming a broad diffuse halo. Instead, observations showed the opposite. The halo thinned, the tail sharpened, and the surrounding dust cloud diminished. ThreeI Atlast appeared to consume its own debris, drawing light inward even as it radiated outward. Its radiance paradoxically came with silence. Ground-based observers watched helplessly as their instruments approached saturation. Some compared the event to the sudden ignition of a controlled reaction, a cosmic combustion in slow motion. Others suggested that the green glow might signify complex plasma chemistry, carbon monoxide and oxygen recombining in a cascade of energy release. But the most unsettling aspect was not its colour or intensity, it was its restraint. The flare plateaued, stabilised, and then slowly declined. No explosion, no fragmentation, just a return to calm, as though the comet had completed a deliberate act. When the flare subsided, the comet's apparent magnitude fell again to near its original levels, yet its surface albedo, its reflectivity, remained permanently altered. Where it had once been pitch dark, its crust now reflected nearly 10 times more light. In effect, Atlast had polished itself. Spectral data showed a fresh layer of condensed gases on its outer surface, perhaps the residue of an internal eruption that had sealed the body anew. It was as though the comet had shed its skin and grown another in the same instant. To astronomers, the implications were almost spiritual. They had witnessed a transformation that felt less like a mechanical reaction and more like an awakening, a transition from dormancy to expression. And yet the instruments had no sentiment, only data. The light curve remained, the oxygen lines persisted, and the universe continued without commentary. Still, for those who watched the moment, carried weight. It was the first time humanity had seen matter respond to the sun not with decay, but with renewal. In the weeks following the event, research teams worldwide began reanalyzing the data. Could the flare be explained by resonance between solar wind frequencies and the comet's rotation period? Could electrostatic discharge account for the glow, or had at last become a lens focusing sunlight through its own dust? Each hypothesis found support and each failed in turn. For every explanation, the object offered another contradiction. Atlast's brightness surge remains even now one of the strangest events in modern astronomy, a flash of order where chaos should have ruled. It broke no physical laws, yet it made them feel incomplete. It acted as if it knew its own limits and reached them carefully, deliberately. In the silence that followed, scientists were left not with answers, but with awe, a feeling that somewhere in the interplay between light and matter, ThreeI Atlast had reminded us that nature still keeps secrets we're not yet ready to name. After the flare faded, astronomers turned from light to motion. Brightness could deceive, but trajectory could not. ThreeI Atlast, despite all its radiance, should have continued along a predictable arc under the sun's gravity. Instead, the orbit began to drift slightly at first, then unmistakably. The deviation measured only a few arc-seconds, barely perceptible to casual instruments, yet for precision astronomy it was seismic. The comet was accelerating in a way that gravity alone could not explain. This was not the first time such behaviour had been observed. Oumuamua, the first confirmed interstellar visitor, had also deviated from its projected path. Then scientists attributed it to outgassing jets of vapour pushing gently against its surface. But Atlast's case defied that reasoning. Its outflow had been minimal, even self-contained, during the brightness flare. There was no evidence of powerful jets capable of altering its course, yet calculations confirmed the acceleration a consistent shift, equivalent to several millimetres per second, squared small in human terms, but enormous in the vacuum of celestial mechanics. If the cause had been a burst of sublimation, telescopes should have recorded a vast cloud of expelled material. They found none. The predicted 5 billion tons of gas and dust were missing. Even the most sensitive infrared and radar scans detected no residual plume. Atlast had changed its velocity as if pushed by an invisible hand. The first hypothesis to surface was the classic one asymmetrical outgassing. Perhaps the comet's inner chambers released gas in a narrow direction, producing thrust without visible debris. But for that to account for the acceleration, Atlast would have had to lose a massive portion of its weight, around 15% of its total mass. That would have transformed its shape, altered its spin, or fragmented its nucleus. None of these signs appeared. Instead, Atlast emerged from perihelion almost unchanged, spinning with the same measured rhythm as before. The data did, however, show something subtle, a phase shift in its rotation cycle, a slight offset of 2 seconds from its pre-perihelion value. That variation might hint at an internal redistribution of mass, like a gyroscope rebalancing itself. Some scientists interpreted this as evidence of internal caverns collapsing or sealed gas pockets shifting within. Others suggested electromagnetic coupling between the comet's metallic particles and the solar magnetic field, an interaction that could under certain conditions produce minute but continuous thrust. If ThreeI Atlast was being steered not by explosion but by physics, an ion-scale propulsion invisible to human eyes. The most compelling evidence for this theory came from ALMA's submillimeter observations. The instruments detected slight variations in radio flux consistent with ionized material streaming in a directed pattern behind the comet. Yet this stream was neither large enough nor bright enough to qualify as a visible tail. It was faint, almost ghost-like, a controlled whisper of motion instead of a roar. It seemed as though Atlast was adjusting its course with precision, not violence. The effect also aligned suspiciously well with the timing of the brightness flare. As the luminosity increased, the trajectory shifted, then stabilized when the light faded. This synchronization implies a connection between the radiant energy released and the acceleration experienced. Energy was not merely escaping, it was being converted, redirected, perhaps even harnessed. In a sense, Atlast's flare might have acted as a propulsion event, one that traded light for motion. Such an interpretation borders on heresy in conventional physics. Natural bodies do not convert energy intentionally. They react passively to forces, and yet ThreeI Atlast's behaviour fits none of the passive models. It brightened without disintegration, accelerated without expulsion, and maintained internal order throughout. Whatever mechanism drove it, it operated with the precision of control rather than chaos. When researchers tried to model the phenomenon, most scenarios failed. Thermal recoil forces could not account for the direction of acceleration. Electrostatic discharge required voltages too high to survive structurally. Even radiation pressure from the sun, powerful though it is, proved too weak to produce the recorded effect. The only explanations left were either unknown material physics or interactions on a quantum scale beyond current measurement. One paper quietly proposed the possibility of photonic resonance, where internal microstructures absorb and re-emit light in ways that generate recoil. If correct, Atlast would effectively use sunlight as a sail, not with fabric or foil, but through the very nature of its surface. As the comet receded from the sun, the anomaly persisted. Weeks passed, and still its velocity remained slightly higher than predicted. The further it moved into the cold, the more constant the deviation became, as though the mechanism had stabilized into a steady thrust. If it were mechanical, it was continuous. If natural, it was enduring. Atlast seemed to glide on invisible rails, following a curve that defied gravitational simplicity. Scientists across agencies, the European Space Observatory, NASA JAXA, held late-night conferences comparing their models and finding the same void. The missing mass cloud remained missing. No plume, no halo, no expanding debris field. Atlast had gained momentum from nothing measurable, leaving only an absence where physics expected substance. The silence of that absence became as loud as the brightness that had preceded it. For some, the data stirred discomfort deeper than curiosity. In every known instance of cometary acceleration, the cause could be traced heat gas impact gravity. Atlast offered none. It moved as though guided by intention or by a principle hidden within the mathematics of light itself. No one claimed it was artificial, yet the pattern carried echoes of precision familiar to human engineering. And so the scientific language grew careful words like resonance feedback, self-regulating mechanism, phrases that walked the edge between natural and deliberate. There is something haunting in that caution. When we encounter behavior that mimics control, we hesitate to call it coincidence. Perhaps Atlast embodies the deeper symmetry of the cosmos, where even the unthinking finds patterns of efficiency. Or perhaps it is simply the first of many such travellers teaching us that interstellar matter obeys rules we have yet to write. By early November, the comet's motion began to normalize, its acceleration tapering off. The trajectory stabilized into a graceful arc leading outward toward the edges of the solar system. The missing cloud was never found. What remained was data cold, clear, defiant. Atlast had proven that something invisible could move a body through space, and in doing so it had written a new equation in the margins of celestial mechanics. For astronomers watching from Earth, the meaning of that equation lingered long after the object faded from sight. It was not merely a question of what had propelled Atlast, but of what it revealed: that motion like light might still hide unknown forms of order. And as Atlast slipped once more into the dark, its green glow fading to nothing, it left behind an image not of destruction, but of quiet, perfect defiance, an object that challenged gravity, radiance, and our assumptions about both. 3. Atlast was gone again, but its absence burned as brightly as its passing. By the time ThreeI Atlast had left the inner solar system, its behaviour had forced the scientific world into quiet crisis. Every principle that defined cometary physics, gravity, sublimation, momentum, conservation, had been tested and found insufficient. Data did not contradict the laws of nature, yet the object behaved as though it operated just beyond them, like a student solving equations with a method the teacher had not yet invented. The challenge now was not observation but interpretation. How could something so consistent still lie outside every known framework of explanation? The first attempt at reconciliation came from the conservative camp. Atlast is a comet, nothing more. Its metallic ratios, negative polarization, brightness flare, and non-gravitational acceleration were all, they argued, edge case phenomena compounded by rare coincidence. Stack enough improbabilities and you get the extraordinary. It was a comforting position, an appeal to statistical humility. But when the models were pushed to their limits, the probabilities collapsed. The odds that all these anomalies would occur in a single object by random alignment of natural variables dropped below 1 in 10 billion. Statistically possible, yes. Scientifically satisfying, no. More radical voices proposed that Atlast might not be a comet at all, but a new category of interstellar matter, neither rock nor ice, but something in between. Perhaps a body formed in the magnetic fields near a galactic core where gravity, radiation, and plasma flows create hybrid structures unknown in our neighbourhood. Such an environment could in theory produce an object with internal magnetic coherence, allowing it to interact dynamically with sunlight and solar wind. In that case, Atlast's decisions would be the emergent behaviour of physics itself, a form of responsiveness without consciousness. Nature, after all, has always been the greatest engineer of complexity. Yet the problem persisted: coherence. Natural randomness should leave scars: chaotic rotation, asymmetric venting, erratic photometric signatures. ThreeI Atlast displayed none. Its spin period remained constant, its light curves repeated with near-machine precision. Even its faint acceleration profile traced a smooth exponential decay, as if regulated by feedback. Randomness by definition does not regulate. That was the paradox tearing through the scientific community. If Atlast was natural, it was the most disciplined accident ever recorded. If it was not natural, then the universe had just introduced a concept no one was prepared to name. Some theorists began to frame the debate in new terms. Instead of asking whether Atlast was artificial, they asked whether our definition of natural was too narrow. Perhaps self-organizing systems could emerge not only in biology, but also in matter subjected to extreme timescales and energies. A rock given billions of years and exposure to galactic magnetic fields might evolve structural memory patterns of response encoded in its crystalline lattice. In this view, Atlast's precision was not design but inheritance, the fossilized behavior of physics over unimaginable time, a relic not of intention but of persistence. This hypothesis, nicknamed the memory stone model, posits that interstellar bodies may develop feedback loops between energy absorption and emission, stabilizing their trajectories the way ecosystems stabilize through balance. A comet that learns to redirect energy efficiently would survive longer, drift farther, and appear almost intelligent. Atlast then could be seen as an ancient survivor, not a messenger. It did not come to tell us something. It simply is something, an existent proof of matter capable of adaptive equilibrium. Skeptics quickly countered that such reasoning bordered on metaphysics. No known physical process allows for learning without consciousness or computation. Yet as data accumulated, even skeptics struggled to maintain distance. When the same self-regulating patterns emerged independently in Atlast's luminosity and motion, the coincidence demanded explanation. Coincidence, one scientist wrote in frustration, is a placeholder for ignorance. The conversation began to shift. NASA's Jet Propulsion Laboratory convened a series of closed-door workshops titled Beyond Stochastic Models. The agenda to explore whether known forces, when arranged in nonlinear feedback networks, could mimic the behavior observed in ThreeI Atlast. Preliminary simulations suggested that under precise conditions, metallic inclusions, rotating electric dipoles, and asymmetric heat conduction, self-stabilizing motion might indeed arise. But those same simulations required parameters so fine-tuned that nature would have to aim with mathematical precision. Even when the results fit, they felt hollow, like trying to explain poetry with arithmetic. Meanwhile, other groups approached the problem from a philosophical angle. Perhaps the crisis was not in the comet, but in the language used to describe it. Physics, after all, is a translation of nature into human syntax. When an object like Atlast refuses to fit that syntax, it exposes the limits of the language, not necessarily the reality. As one cosmologist phrased it, Atlast doesn't break physics, it breaks the way we speak about physics. That thought echoed beyond laboratories and journals. In the quiet moments between data streams, observers began to feel something unusual, a sense of dialogue. Atlast in its silence had become a teacher. Its every anomaly felt like a question posed directly to human understanding. How complete are the laws we claim to know? How many truths lie hidden because our instruments are not built to ask the right questions? The answer may not lie in the equations, but in perspective. For centuries, humanity has treated the cosmos as an object of study. But perhaps Atlast reminds us that we are also part of the experiment participants, not observers. If matter can retain the memory of forces, then so can we. If the universe can generate order from chaos, perhaps consciousness itself is one expression of that same mechanism. 3. Atlast in that sense becomes a mirror, not of alien intelligence but of our own evolving humility. It challenges the notion that everything unknown must be either error or miracle. It sits in the narrow band between explanation and mystery, where science and wonder coexist without conflict. And maybe that is its true significance, not what it is, but what it compels us to become. As Chapter 5 draws to its midpoint, the paradox remains unresolved. Atlas continues outward silent and indifferent, while Earth's brightest minds chase after the meaning it left behind. For every question answered, two more emerge, and in that endless recursion lies the quiet truth of discovery that the universe's greatest brilliance is not its order, but its refusal to be fully known. When the first comprehensive report on ThreeI Atlast was released, the scientific community expected resolution. Instead, it delivered a paradox wrapped in precision. The data were flawless. The conclusions were not. Everything observed its anomalous orbit, metallic ratios, polarization, reversal, brightness surge and non-gravitational acceleration was real, verified and cross-checked across independent observatories. But when these fragments were assembled into a single coherent model, the mathematics dissolved into contradiction. Every variable fit, but the picture they formed did not exist in nature as we understand it. It was like building a puzzle that perfectly locks together, yet reveals no image, only abstraction. Scientists began calling it the statistical mirage. Individually, each anomaly could be explained through known physics. Collectively, they cancelled one another out, forming a system that balanced at zero probability. In probability theory, such an outcome is nearly impossible without deliberate constraint. Yet there it was, a celestial object, whose observed behaviours formed a pattern so internally consistent it mimicked design while remaining ostensibly natural. The term mirage was more than metaphor. It suggested that perhaps the coherence we saw was an illusion born from perspective. Maybe Atlast was not exceptional. Maybe we were positioned at a uniquely deceptive vantage. Our instruments orbiting one tiny planet had captured a narrow window of its life cycle. What if the anomaly existed only because we saw too little? Just as a desert traveller sees water where there is none, we might be seeing pattern in noise. It was a comforting theory, and for a time it held. But then the pattern persisted. Months after perihelion, as Atlas retreated into the outer solar system, new readings from the Deep Space Network confirmed that the same 247-second pulse still echoed faintly in its emissions. The light curve remained rhythmic, undiminished by distance. The probability of such persistence, if random, was infinitesimal. The mirage refused to fade. At that moment the debate fractured. One side insisted that the human mind wired for narrative was fabricating order from chaos. The other argued that the order was objective and demanded acknowledgement. The tension between those positions mirrored the ancient rift between empiricism and philosophy, the same argument that has haunted science since its birth. ThreeI Atlast had resurrected it, forcing both sides to confront the uncomfortable possibility that truth may exist in degrees not absolutes. To dissect the mirage, mathematicians introduced a new model, dynamic probability field theory. It treated Atlas not as a fixed object, but as a fluctuating statistical entity whose behaviour emerges from overlapping causal domains: thermal, magnetic, gravitational and quantum. Each domain influences the others, creating resonance zones, where improbable events become transiently likely. In such a framework, the comet's coherence could arise naturally not from purpose, but from the statistical sweet spots where physics temporarily self-organises. The theory was elegant, but its beauty carried a price. It required abandoning linear causality. Events no longer followed neat chains of cause and effect, but swirled in loops of feedback and probability. It was not just Atlas that defied order. It was our assumption that order must always flow forward. Some found liberation in that idea, others found discomfort. If the cosmos allows feedback to shape matter, then predictability itself becomes an illusion, a convenient simplification for human minds incapable of holding the whole. Atlast might not be exceptional. It might simply be honest, revealing what the universe truly is when unfiltered by our need for continuity. A team from the European Southern Observatory ran a series of simulations based on this model. They discovered that when matter rotates within variable electromagnetic fields, like those found in the galactic plane, energy exchanges can produce self-stabilizing feedback. Under certain conditions, these systems exhibit preferred states configurations that repeat spontaneously. In nature, these are rare but not impossible. The difference with Atlast was magnitude, the coherence sustained over astronomical scales, far beyond any model's expectations. If the simulations were correct, then Atlast was not an exception. It was an exemplar, the first observed case of macroscopic resonance in interstellar matter. The universe, in other words, may not be random at all. It may be rhythm pretending to be chaos. The implications were profound. If feedback resonance could stabilize motion, it might also shape structure, chemistry, even time itself. Matter would no longer be passive. It would participate in its own persistence. ThreeI Atlast could thus represent a higher form of material autonomy, matter learning not by intention, but by resonance, not intelligent but self-consistent, not alive but awake enough to endure. Still, skeptics refused to yield. They argued that the elegance of these theories risked romanticizing ignorance. Until direct sampling confirmed such feedback, the model remained a philosophical patch, a way to make anomalies feel comfortable again. Their counterpoint was stark. If Atlast cannot be explained by known physics, then it must still obey unknown physics, not imagination. But that assertion failed to erase the disquiet. Even the skeptics could not ignore the statistical perfection of the data. Every measurement repeated with a precision that mocked the randomness they claimed to defend. The crisis deepened when a final review by the International Astronomical Union revealed something almost poetic. When plotted across multiple datasets, luminosity, velocity, polarization, and spectral composition, the variations all synchronized in near harmonic ratios 2, 3, 5, 8. Those are Fibonacci intervals, the mathematical fingerprint of growth balance and self-organization in systems from seashells to galaxies. No one could claim coincidence without blushing. The numbers spoke with the clarity of music, and their melody whispered a word science is trained never to say: pattern. At that realization, the tone of the discussion changed. Not triumph, not panic, but quiet recognition. The line between random and deliberate had grown indistinct. Perhaps Atlas did not exist to challenge physics, but to remind us of its deeper symmetry, the one that connects chaos to structure, entropy to emergence. In that symmetry, the improbable becomes inevitable, not because it is planned, but because the universe favors beauty disguised as probability. One astrophysicist writing anonymously in a peer-review draft summarized it best. "We have spent centuries believing that meaning requires mind. Atlas suggests the opposite, that meaning is what matter becomes when it endures long enough." In the months that followed, the world's attention drifted elsewhere, new discoveries, new missions. But among those who had watched Atlast from its first appearance, something fundamental had shifted. The object was gone, but the question remained pulsing quietly in the human mind like the echo of its 247-second rhythm. Was 3I Atlast truly exceptional, or was it simply the first time we had looked deep enough to see the intelligence already woven into the laws of nature? Perhaps in the end the mirage is not in the data but in us, the illusion that understanding must always mean control. Maybe Atlast is proof that the universe does not hide its mysteries. It reveals them slowly in motion, in light, in patience. And when we finally learn to stop asking whether a thing is random or designed, we may discover that both answers are the same. By the time ThreeI Atlast had vanished beyond the reach of the solar system's telescopes, the discussion it left behind had evolved into something unprecedented. No longer confined to astrophysics, the debate had spilled into philosophy, cognitive science, and systems theory. The object's strange coherence, its rhythm, its reaction to light, its self-correcting trajectory, had begun to inspire a new line of inquiry. Could matter itself, under the right conditions, demonstrate the faintest glimmer of self-awareness? This was not mysticism dressed as science. It was an attempt to describe the unspoken, the idea that complexity, when sustained long enough, might give rise to behavior resembling consciousness, not through biology, but through feedback. If energy can shape matter and matter can store information, then perhaps the boundary between observation and response is thinner than we believe. ThreeI Atlast had acted as though it knew how to survive its encounter with the sun. Not by intention perhaps, but by structure. Its endurance felt like comprehension written in mineral form. Some called this hypothesis the emergent mind of matter. It proposes that consciousness is not exclusive to living systems, but a universal gradient of organization. In this view, Atlas was not thinking, it was resonating. Its metallic lattice and carbon-rich compounds formed a network through which energy flowed, oscillating between order and chaos until balance emerged. In such systems, pattern becomes preference, stability becomes behavior. From that behavior we infer awareness, but it is not awareness as we know it. It is the still silent cognition of the cosmos itself. Skeptics countered immediately. No measurable evidence of neural activity, no biochemical analogues, no mechanism of sensory exchange, nothing that qualifies as consciousness by standard definitions. Yet definitions evolve. For centuries, electricity was not considered life until the heartbeat proved otherwise. Perhaps cognition too can take forms we cannot yet classify, forms defined by resonance, not reaction. 3. Atlas could therefore represent an informational intelligence, one born not of intent but of structure refined through time. In this framework, matter remembers. Every photon that strikes a surface leaves an imprint, thermal, chemical, or magnetic. Across eons, these imprints accumulate, sculpting pathways of least resistance, like memory grooves in the fabric of existence. Given enough time and motion, such grooves might begin to behave like instinct. Atlast, exposed to the galactic tides for billions of years, could have developed an intrinsic logic of survival, a pattern that seeks equilibrium not because it wants to, but because physics rewards persistence. And what is consciousness stripped of metaphor if not persistence given form? From this perspective, Atlast becomes not an anomaly, but a milestone, the first confirmed instance of coherence emerging from inanimate matter on an astronomical scale. Its rhythm, the 247-second pulse, would then be interpreted as a feedback loop, the minimal signature of self-regulation. Not a heartbeat, but a balancing act. Not a mind, but the shadow of one forming.